What basic equation do we always write when we deal with a circular orbit? Explain where this equation comes from. Okay, so the basic equation that we always write is we relate the gravitational force to being the force that causes the circular motion. So we have gmm over r squared, which is Newton's law of universal gravitation, where g is a constant. I guess we have a big M in there. Big M is the central body, little m is the rotating body, and r squared is the distance between them, usually the average distance between them, if it's not a perfect circle. We have all of that equals the centripetal force, mass times centripetal acceleration, and centripetal acceleration is v squared over r. F equals F. That's it. Another equation that you could write would be using Newton's law of universal gravitation and setting that equal to m times 2 pi r over the period divided by r, and all of that stuff in the numerator is squared. So it becomes 4 pi r squared over t squared divided by r. This right here, we can pull out that period, and when we solve for this, we get that relationship where t squared is going to be proportional to r cubed. This is Kepler's third law of planetary motion. This is actually how Isaac Newton proved this formula 200 years later. So Johannes Kepler and Tycho Brahe's data was able to determine this relationship, but it wasn't able to be proved mathematically for 200 years when Isaac Newton came around and fixed that. An object mass m orbits a planet radius big M with orbital radius big R. Use the equation you wrote above to derive equations for the speed the object has as it orbits. I'm going to rewrite that equation that we just got from over there, which was gm big M over r squared equals mass times 2 pi r over t over r, and all of this stuff in the numerator is squared. So that's going to give me gmm over r squared equals m times 4 pi r squared over t squared divided by r. So we have the fraction in the numerator. That stuff's going to be too heavy, so that t squared is going to drop down to the denominator, which is going to allow me to cancel my r here, cancel that r over there, and we're trying to get t all by itself. So I'm going to divide little m from each side. Goodbye, little m. It's been real. We have 1r over here in the numerator, so let's go ahead and divide r on each side. So that'll go away, and this is going to be another r over here. Rewrite this because it's getting a little messy. Over r cubed equals 4 pi over t squared. Now I have a proportion. I can just multiply each side by the reciprocal, and I'm going to get t squared over 4 pi equals, oh, that m went away. Nice try. And I said reciprocal, Mr. Scapetus. That's the flipped fraction. R cubed over gm. Multiply each side by 4 pi. So I have t squared equals 4 pi. Don't let that pi squared fall off there. Woo! Did you see what I just did? Don't do that. You have to square every single term here. I knew it was wrong because by the time I got here I knew this is going to end up being 2 pi after I take the square root, but maybe you don't know it that well. Be careful with your math. That's my advice. That's the lesson from my Great mistake. R cubed over gm. Now we'll take the square root of each side, and what we get is t equals 2 pi. We can pull out the stuff that can actually be square rooted, times the square root of r cubed over big G times big M. What the heck is that? That's the period for the object that's orbiting. Actually, we accidentally might have got ahead of myself over here. 2 pi times square root r cubed over G times M. The speed that the object has to orbit, I should have stopped a little bit earlier, but let's go ahead and do it. Gmm over r squared equals m times v squared over r. This is a lot less labor intensive here because I'm going to multiply each side by r, so that r is going to go away, that r is going to go away, divide by m, that m is going to go away, and v is going to be the square root of gm over r. There you go.